Please like and leave a heart. Please.
There we go. Unmute. Hey everybody, and welcome to the Vidor Locksmith Show. I'm your host David Gibson, where we are unlocking the secrets to success in the oil and gas industry. One interview, one technical presentation, and obviously one technical screw up at a time. Thank you guys so much for being here with us on this amazing Friday. We've got an awesome show for you guys. Can't wait to be able to get this one underway, as this is something near and dear to my heart. So for everybody out there, please let me know where you guys are watching from. Love to be able to give you guys a shout out here on the screen as we get going. I know that there's already a handful of people already taking off here in the comments. And as of course, our previous guest here on the show, Mr. John DeWart, saying good morning from sunny Elkhart Lake, Wisconsin. Thanks for being here, sir. Do appreciate it. Soren says good evening from Copenhagen, Denmark. Great to have an international show on here today. Good morning from Dallas, Texas. Looking forward to today's talk. Mr. Pete Stetson, part of my race car team. LinkedIn user from the British Isles. Awesome to have you here. Soren asks, is this a replay of our previous session? No, this is live. This is the one and only. Waiting for the snow to come here in Denver. Whew. I definitely don't think that's what I'm looking for. Mark, you're supposed to get dumped on. Is that correct? Let's see. That's the concern. A lot of preemptive closures of schools and whatnot. All right. John helping us out, telling them it's live. So we're up to date there. All right. Robert Brown from Lafayette is here. Thanks for being here, sir. Michael Cotton from Abu Dhabi after ADIPEC. Oh, yeah, guys, let me know. How was ADIPEC this week? Obviously, really big stuff going on there. And then we've got Taylor Daughtry tuning in from Houston. Thank you guys all for being here. We do appreciate it. All right. If you guys get the chance while watching today, be sure to put in hashtag AIDRILLER. This is our sponsor for today. We'll be giving away some cool swag at the end of the show. We've got a 3D printed drill bit. It looks orange in the video, but that is actually red. So if you like the color red, got those. So be sure to put in hashtag AIDRILLER now and throughout the show. We'll get that, and you'll get entered in for the giveaway at the end of the show. With that said, let's go ahead and play our quick clip from AIDRILLER. Thank you to our sponsors. Girl, I wanna hear you whisper it. Girl, I whisper it. Girl, I wanna hear you whisper it. All right, there we go. A couple of you have already done it. Put in AIDRILLER. Thank you guys for doing that. I do appreciate it. Helps keep the show going because obviously some of you really enjoy the show. Something I have done in the past, but I'm going to try to start doing again. If you would please, to be able to help promote the show, there's clicks, there's links, there's all the things that you can do, like, subscribe, all that. But what I would prefer is if you would just tag somebody in the comment section that you think would get something valuable out of today's presentation. You can do it now, do it later. Just tag somebody, then obviously they will see that they're tagged in it, get the notification, and come over and hopefully maybe watch it for a couple of minutes. So probably one of the best ways to be able to kind of get the show going and, one, keep the sponsors happy. And if sponsors happy, they're helping out, and it makes this all a lot easier for me. And then obviously I can keep providing great content for you guys. So there's my sales pitch for the day. All right. Without further ado, let's put there we go. Put that back up on the screen and welcome in our guest of honor today, John Huycke. John, thank you for being here, sir. Really appreciate it. I know you've got a presentation, so I'll go ahead and get out of your way, let you go ahead and present. And then, guys, if y'all have any questions throughout this, go ahead and throw them in. We'll answer some of them as we're going along. If we get too far ahead, then we'll come back, we'll star them and answer them all towards the end. So there we go. Put that up on the screen, and then I'll step out of the way. And then, John, it is all yours, sir.
Thank you, David. Just a little bit of background. From 17 to 23, I was working for PDC Energy, and at PDC, I was involved with the planning and execution of 8 U Laterals in the Delaware Basin. In the last year, I've effectively been retired, but tracking the progress in the industry with U Laterals. And with that, we'll get into what's up with U Laterals. Okay, we're gonna.
Oh, here.
Can you work it off with this here?
You should be able to.
There we go.
There we go.
Okay, so the first thing is that U Laterals are really predicated on stranded sections. And what is a stranded section? You can see there that we have a lease in the middle of this big block. An operator owns this thing, but he doesn't have any mineral rights around it. So when you drill a lateral, you can only drill a 1 mile lateral. So I've kind of given the secret away. What can you do? You can come up here, turn it around, and come back the other way to make a longer lateral. Here we're going to take a look at a stranded section. So now we got 2 1 mile laterals in there, and what can we do to make that better? And we bend that thing around, we come back and come back to the original well location effectively. And the next step is really important. We get rid of the intermediate hole section on that second well. And there's a big cost associated with that. When we get that out of there, the economics go way up. And I'll cover that in a little bit. First, U lateral terminology. There are a couple of things that are important here. The yellow is the vertical hole, so that's everything it takes to get to the kickoff point. The brown is the curve. The outgoing leg is blue. And this is what we've done thousands and thousands of times in the US. But here's what's new. The red is the turn, and it turns the wellbore around in azimuth by about 180 degrees. And then the green is the return leg. The key thing is to keep the curve idea in our head and the turn idea in our head so we don't get them mixed up. So economics, this is what's really driving the entire concept of the U lateral. So I'm going to go through this like an engineer on what this actually results in. So we have 3 scenarios here: 2 1 mile laterals, a U lateral, and a 2 mile lateral. In a stranded section, these first 2 are only options, but I want to compare the economics. So for the first situation, 2 1 mile laterals, land at 70 degrees, drill to 100 feet from the lease line, do that twice, it gives us 9,400 feet of completed lateral footage. Do the same thing with the U lateral, land at 70 degrees, get 30 degrees into the turn, 30 degrees out of the turn, and then 100 feet from the lease line, we get 9,200 feet. And if we could do a 2 mile lateral, we end up with just about 10,000 feet of lateral. So this is a graph of the same thing. Here's 9,400 feet, 9,200 feet, and 10,000 feet. And now I'm going to go through the costs of these operations. The first one being drilling. So if you drill 2 1 mile laterals, you're somewhere to the tune of $7 million. And this is Delaware Basin. So every basin is going to have a different cost structure, but that's what it is for the Delaware Basin, 7 7/8 hole size. If you're to do 1 U lateral, you're just under $5 million. And if you're to do a 2 mile lateral, you're just over $4 million. So where are the savings coming from here to here? Well, we've eliminated an entire intermediate hole section. So we got rid of surface hole, surface casing, surface cement, intermediate hole, intermediate casing, intermediate cement, and the landing to get us to horizontal. Completion costs, likewise, there are savings there. 2 1 mile laterals, about $6 million. A U lateral, $5 million, and the 2 mile lateral, a little bit more than $5 million, just because you have that extra footage between the 9,200 feet and 10,000 feet that you're completing. And where do those savings come from? Going from here to here, we're looking at eliminating a tubing string, getting rid of trips, and then the rental duplication because you have 2 wellheads with 2 1-mile laterals and just 1 wellhead with a U lateral. And finally, all-in capital costs, 2 1-mile laterals, about $14 million, $10 million for a U lateral, and likewise $10 million for a 2-mile lateral. And this cost includes facilities. So this is a different color here because this is where the rubber hits the road. The economics on 2 1-mile laterals has about a 23% rate of return. The U lateral is 53% rate of return. These are the options in your stranded section. And if you had the option of doing a 2-mile lateral, the rate of return would be 70%. So if you have 2 sections put together, it doesn't make sense to drill U laterals. You do a 2-mile lateral because you get a better rate of return. So here's where we're at. Rate of return increased 25 to 40%. Cost reduction, $3.5 to $4 million is what I had seen. Just so you know, I'm not crazy. Matador, at the end of last year, came out and publicly stated that their 2 U laterals, they saved $5 million for each one of them. And just ask your friends that are drilling U laterals. It's about the economics. I'll show you the slide that Matador put out there. And you can see that they originally had 4 1-mile laterals, changed it to 2 U laterals, and they said they saved $10 million or $5 million a well, which is a huge number. Recently, there was some new information out, and they're claiming that they're saving $3 million a well, but still a very big number. So U lateral history, here's where we are in the industry with spuds. In 2019, Shell drilled the Neely well. Chesapeake did the Geo well in 2020. Chesapeake did a second well in 23, and PDC did 3 wells. And then we just have an exponential increase in the number of wells that are being drilled. So 2023 was 27. This year, we're up just short of 30 wells. And, you know, this isn't going to stop. I've found 63 permits out there on the internet for wells that haven't been drilled yet. And here's what the activity looks like by basin. Over here is the Delaware. There are a lot of wells in it. It's a difficult place to drill. It's an expensive place to drill. The intermediate hole section, you set casing, that makes it even more expensive. So there's been a lot of activity there. The Eagle Ford, you don't set intermediate casing, but there have been 15 wells drilled there. DJ is one of the easiest places in the country to drill, and yet people are coming back to drill more and more wells there. And then you can see there are multiple other basins. Most of the major basins in the U.S. are covered with at least 1 U lateral. And this is what the map looks like. So you can see the Delaware has a big chunk of wells, and then we got the Eagle Ford down here and the DJ up here. Midland has got 6. There are a lot more permits in the Midland, the Delaware, the Eagle Ford, and then you have the rest of the country with 1 and 2 off wells in them. So what is going on with the operator well count? You can see that Occidental has drilled 10 wells with U laterals, likewise has PDC. Occidental has done a couple of pads up in the DJ and a pad in New Mexico, Delaware. PDC has done 3 pads in the Delaware and 1 in the DJ. Chesapeake has multiple drills in the Eagle Ford. Matador is a big player here in the last year with multiple pads in both the Texas and New Mexico, Delaware. And Chevron, in just this year, 2024, has drilled 6 U laterals, and one of them here recently was 2 miles up and 1 mile back. That really is a technical achievement. That'll be the first of its kind there. So when it comes to planning for U laterals, one of the questions is, well, what hole sizes can we do? And here are counts for wells out there drilled with particular hole sizes. So you can see that we've got 6-inch all the way to 8 3/4. That is all the common hole sizes in the USA. So when it comes to picking a hole size, if you're comfortable with the hole size, you're covered. There may be some limitations on rotary steerable tools if you pick one over the other, but you're going to be able to accomplish what you want with any hole size. What's that, David?
So jump in here is a pretty good question on the about the previous slide.
Yeah.
Have any U laterals been drilled outside of the U.S.? If not, are any planned?
You know, I don't know if any have been drilled outside of the U.S., but I have talked to an operator that was interested in doing that, and it was in Canada. So they had a particular situation that wasn't exactly a leasehold thing, but limited extent of their formation. So they would effectively be drilling 1 mile of formation, but the economics would improve by turning around and coming back. So I don't know of any, but I know people are considering it.
All right, I'll go ahead and take that one off, and
okay.
Let's heart that one for later.
Okay.
And yeah, now you're back there.
Whoops. Okay, so another question is, well, how far apart do you want to put your legs of the lateral? And this is a distribution of all the wells that I know of. They've gone anywhere from 3,000 feet to 900 feet. There seems to be kind of a magic area somewhere in the middle around 1,500 feet. And the reason is at 1,500 feet, you're getting some reasonable dog legs to the tune of about 7.5 degrees per 100. If you're doing 900, your dog legs are getting pretty big. So you're probably talking 12s. And the problem with doing really big leg separations is you get dead space there that you're having to drill, and you're having to cover it with casing, and you aren't completing it. So it takes the costs up, and there may be some better way to get those legs closer together. And then when it comes to lateral length, what are people doing? There are 2 wells here, and these are PDC wells done in the DJ Basin that were 1.5 miles up and 1.5 miles back. There's another one here, this Pepper well that Chevron had done that is 2 miles up and 1 mile back. So there are a fair number of wells that have extended the mile up and 1 mile back. And it's going to come down to doing your homework, doing the torque and drag, designing your drill pipe and casing running tools so that you can be sure that your operation is going to be successful. When it comes to the shortest length, we're down to a lateral length here of, oh my gosh, it's hard to see here, 7,000 feet. So it was a little bit less than 1 mile up and 1/2 mile back. Now this plot here is just to give you a visual of what it looks like with all these things plotted from the same surface location. And the idea is, hey, the people have been out here doing this. It started in 2019. They've been successful with almost all these wells, but there are also survey files and directional plans out there that engineers can pull off the internet, and then you can start modeling off this information to determine what the torque and drag would be like. It gives you a place to start by using somebody else's information. And then you'll want to do history matches with your torque and drag to your directional plan, and then generate numbers that you can plan by. And I mention that because if your tortuosity is too high, it can make your torque too high or your drag too high. So you want to know what it is going into your well before you actually get there. You don't want to drill yourself into a corner. When it comes to drilling, in my mind, there are 4 main points to drilling success. First one is getting in and out of the hole. And we got a plot over here, a broomstick plot showing tripping in and out of the hole. The next one is capability to drill. You put your BHA on bottom, you're able to put weight on it, you can turn it, and that generates torque. Here's a torque plot, and the torque has to be within the capability of your drill pipe and your top drive system and your iron roughneck. And then a really big one here is getting your casing to bottom. That's what this is. You do all this work drilling it, and if your casing doesn't get to bottom and you leave formation uncovered, you're never going to be able to get back to cover it up with casing. If you have to trip out of the hole and clean up your hole, it just is horrendously expensive, to the tune of $700,000 for your casing, and then another $500,000 for the time to condition the hole and get it ready for another run. Down here with cementing, there are minor changes to that. So the practices that the folks are doing for cementing will either be the same, or there might be a little bit of thinning of the cement, just because you have a little bit more measured depth. But really, I don't think cement knows whether it's going around a turn or it's going in a straight hole. So here is a plot. This is the broomstick plot of tripping BHA. We have measured depth here, and we have hook load here. This is the survey file, so this is a real well bore. And then we have the model data, and I've made some artificial points because I don't have access to the TACO information. In this particular case, you can see we're going in the hole here, and it's nearly vertical, represented by this part here. And then as we go out into the lateral, we have drag as the BHA and drill pipe is being pushed. And then this modeling shows that about this point, it no longer goes in the hole anymore. And that puts us in a little bit of a bind because we haven't gotten to TD yet. But drilling folks know that if you have problems running in the hole, no issue. You rotate your drill pipe. Here we have the same thing, measured depth versus hook load, 0.15, 0.2, 0.25 on the friction factor. And now everything comfortably fits into the common range of friction factors that we see in the wellbore. So this one is pretty easy to get around. If you're not getting to bottom, just rotate your BHA and you'll get there. Here is drilling torque. And this one is important so that you know you have the right equipment on location. Here we have measured depth, and here we have top drive torque. And I'm going to go through the 0.25 friction factor here. So here we are, we're landed out horizontal. This is the outgoing leg, and that is represented by this right here. Then the slope increases as we go around the turn, because that drill pipe is flexing in that hole and generating more side forces, so the friction goes up. And then we have the return leg here, and that is represented by a little bit lower slope on the torque here. This shows the tortuosity in this wellbore, so pretty low tortuosity shallow to the kickoff point, and then higher tortuosity there. You can see, if you look closely, this is the curve. This is the first part of the turn. This is the second 90 degree of the turn. And then this is the return leg. Now, I want to focus attention right here. This is the torque at TD, and it's 35,000 foot-pounds. So that is pretty high for something that would be a 2-mile lateral. If you have drilling contractors drill pipe with an NC50 connection, it's rated to 32. And then the drilling contractor would derate it to 28. And then the auto driller would be set at 26, which means when you take that up, somewhere around this depth of 18,000, 17,000 feet, you're having to take weight off of bit and reduce your drilling performance because you don't have torque capability. What's that, David?
I was to make sure you got the cursor on this side or that side.
Is the cursor showing up?
No, because it's on this screen.
Wow, all this time? Okay.
Sorry.
Let me go over that again. So,
or no, I think. Sorry. No, that was my mistake. I believe it was showing up.
It is showing up.
Yeah.
Okay. Good deal.
Okay. Wait, go back over to this one with it though.
Yeah.
Yeah. There we go.
Do I need to be over here?
Yeah. Just as long as the cursor's here, then it'll show up on the screen.
Ah, shoot. So all that previous, it wasn't showing up?
I believe it was. I don't know. Maybe somebody that's watching can let us know.
Okay.
If it was there or not.
Okay. Well, bum deal. So again, here is the torque that we have at TD 35.
Okay. They said they could see the cursor. Okay. Just make it sure.
They can see it now
Yeah.
or see it before?
Yeah.
Okay. So the issue is drilling contractors pipe 32, derated to 28. 26 is what the auto driller set at. When you get to this point, 17,000 feet, now you're having to take weight off of the bit so that you can continue to drill ahead with the torque that's within the drill pipe's capability. The additional issue is that if you have NC50 connections and you have any downhole makeup, trips can really be a bear with roughnecks up there having to beat on the connections with the sledgehammer to get it to break. So that is the point associated with the iron roughneck. You need to have a capable iron roughneck to break these things out. Over here I have data points for torque while sliding, and you say, well, where is all this torque coming from? That is another key part of this thing, is that on these U Laterals, you need a lot of friction reduction, and one of the methods of friction reduction is to use an oscillator. So you're rotating this thing to the right and rotating it to the left, and this is the kind of torque that is generated. So that is a part of it also.
Okay, so what I realized is when the cursor's still here,
yeah,
it disappears on this screen, but they're still able to see it there. So that's why I got concerned.
Okay.
So they were able to see it the whole time. So we're good.
So I can
I got it. No. Keep it over here.
Okay.
But then they'll be able to see it on the screen. So
okay.
We're good.
Okay. So here is a sensitivity analysis on tortuosity, and this is important. So we've got our base case here, and we took that base case and added a lot of tortuosity to the lateral and to the curve. And over here we have overlaying on them the base case torque and the high tortuosity in the lateral case. And the key thing here is we go from about 38,000 foot-pounds of torque to 40,000 foot-pounds of torque in this case. So it isn't terrible. But we're going to take a look at a different case here, and this is where we go from base case to added tortuosity, but we add the tortuosity here in the vertical part of the hole, and it is not outrageously high. There is no added tortuosity here in the lateral, and all of a sudden we go from that 37,000 foot-pounds of torque up to something that was off scale. So it's an additional 11,000 foot-pounds of torque to 48, and 48 is untenable. Your drill pipe won't be able to take that. The combined tension and torque on the tube is going to be a problem, in addition to your common high torque drill pipe is rated to about 48,000 foot-pounds. So that means that we need to be careful about tortuosity in certain parts of the hole. And when it comes to torque, it is shallow, and that makes sense because our drill string is hanging down vertically with a lot of tension, so any deviation has a lot of side force, and that side force is creating a bunch of friction. So the next one is running casing, and again I say this is really a big deal. In this case we have no casing flotation. We're running it in this wellbore. These models are based off of this survey file, and we can see as we go in the hole, this is the vertical represented by this section right here, and then we're going out in the lateral with reduced weight at the top, and that is to push the casing into the lateral. In this particular case, it says somewhere around 20,000 feet we're going to have some trouble getting our casing to bottom, and that is a big issue because of the potential loss formation or tripping the casing out and the financial losses of junk casing and the time associated with cleaning up the hole. So what can we do about that? The first thing, and this is pretty common in the industry, is just to float the casing in the hole. And this shows the case where we're going in the hole vertically, again right here, and then we're going out into the lateral, pushing it this way. At this point, this is all empty casing going in here with air, and then we put a flotation sub in, and with the mud on top, it's shoving the casing in the hole. Now we take a look at this. Again, we have 0.15, 0.2, and 0.25. Most of what I've seen, the friction factors are between 0.15 and 0.25. So this says that we're going to be successful here. So that is a mitigation that will work. It just is something that you need to plan for. You need to have the right threads on your flotation sub. And, you know, it's not something you can do overnight. So you got to get somebody to do that in advance. Kind of the gold standard, if you've got a very difficult situation, is flotation and rotation. Again, same wellbore, but you can see in this particular case with both of them that all of the friction factors will work, and you'll be able to get your case in the bottom in any situation here. So if you have a wellbore profile that's more difficult than this, then rotation may be needed. It's a big deal. You got to check and see how much torque is going to be required to rotate it in the hole. And then you need to make sure that your casing connection is good for it. And then finally, you got to get a case and running tool that will get on that casing and will effectively rotate it in the hole. And you can't have failures with your case and running tool. So you need a high quality tool there. So torque and drag modeling will confirm if the directional plans are feasible. We talked a little bit about dogleg severity sensitivity analysis. You need to do that. I showed the case where with torque, the dog legs high in the hole have a big effect on that. When it comes to running casing, dog legs out in the lateral have a big effect on that. So I'm a big proponent of just running the torque and drag on this so you know what you're looking at. And if you know what you're looking at, you know what you need to control so you can be successful in executing on these wells. The torque and drag modeling will point to your tool joint selection. It will also point to your top drive. You need to have a capable top drive. You don't want to be running the limit there. And I think most of the top drives out there are pretty good now. And then the iron roughneck. You need an iron roughneck that can make and break your drill pipe. Making it's not a problem. Breaking it can be an issue. I talked about that. The plots that I showed you previously had generated data points there. But as an engineer, I want to finish the well. Actually, I want to go ahead and take the survey files as we're drilling the well and put the data points on it to see if there's anything that looks suspicious, so I can tell if the well is behaving like it's been modeled. And if it's not behaving like that, then the question is, what's going on? Do I have wellbore instability? Is there something else that is an issue? And as an engineer, if you got the data and you plot it up, then you can look at it and determine what the values are that are reasonable for friction factors, and then you can better use your modeling. And that's what that says there. Now, I'm going to talk a little bit about BHAs, not very much, but here's an example of a turn BHA. And DDs out there ought to be familiar with this thing because this really looks pretty much like a curved BHA. So we got a mud motor here. It's pretty fast like you would have for a curve. The torque is not as high as some of the warhorse type motors you have for drill and lateral. But you know, the point is directional control here because you have a lot of directional work to do. You take a look at it. Here's the curve right here. So that's 90 degrees. We're up here. Here's 90 degrees and then another 90 degrees. And we're laid out there at a mile horizontally with all the friction in the hole. So it's not an easy directional situation. And DDs will want something that is directionally friendly. This is a directionally friendly motor. Another thing in this BHA is a reamer. And the reamer is used to help dress the hole so that you get rid of something that I've called rugosity, and in the literature is called micro tortuosity. This is tortuosity that you can't see in the surveys, but this reamer can dress the hole and get rid of the edges and ledges and reduce friction while you're sliding. So that I've seen to be important. Right here, we have an agitator. I use those about 2,000 feet behind the BHA, and then a second agitator, another 2,000 feet behind the BHA. And again, we're talking friction reduction. So we have a directional BHA a long ways out there in the lateral. The two agitators are reducing friction in the lateral, and then we have the oscillator on top reducing the friction in the vertical part of the hole and in part of the lateral also. Now here's an example of a return BHA. So we're talking this part of the hole, and it's very similar. The reamer, the agitators, same stuff. The motor is a little bit different in that it's a slower motor with a higher torque capability. And the idea is to put a lot of weight on it, bury the cutters, and have a motor that isn't maxed out turning the bit. So the motor will last the entire run. So this is kind of a summary of it. The drilling of the turn is difficult. You're going to need good DDs. Probably be some trouble doing it, but if you got people that can think on their feet, they'll work around the problems. The assembly that I had talked about was a 2-degree bent housing motor, slick. I've seen ones run with stabilizers on them, and while the dogleg yield is great, there's difficulty getting them to slide. A reamer behind the BHA, agitators, the top drive oscillation, all of these things important to making the directional work go. The mechanics of the turn, so we're out here horizontally and we're sliding a fair chunk of the time, probably greater than 50%, and a hole cleaning is going to be a problem. So that means that we are either going to buy into wiper trips or we're going to be reaming stands down to make sure things keep moving. The second thing is wellbore rugosity. And I've been a part of cases where you slide ahead and then sliding locks up after 500-600 feet. And it takes reaming that section down to get back to sliding. And that is the reamer cleaning up the edges and ledges on the wellbore to make sliding possible again. So those two things beg the question, what about rotary steerable? So rotary steerables have been used to drill the turn, and there are some unsuccessful wells, but there are quite a few wells that have been successful with different rotary steerable systems. So I know two with NeoSteer that did great. One of these was a one and done type of thing where they went in the hole, did essentially the entire wellbore, the outgoing leg, the turn, and the return leg. There are a number of wells with 6 1/8 orbit G2 that have been successful. None of them that I'm aware of that were one and done, but I think they all performed well. There are 3 with G2 that have been an 8 3/4 hole, and then there are a fair number here, 5 wells with iCruise an 8 1/2 hole. So the beauty of this is now you're drilling down, you aren't having to ream the hole, you aren't having to worry about keeping the hole clean, and this results in just great time savings if the tools hold together. And that's what I'm talking about here. With that said, one and done is pretty rare, and that is because these rotary steerable tools are I won't say delicate, but they're not as robust as conventional mud motor systems. And we're putting it in really a pretty difficult drilling situation with all the big dog legs going around the turn. So drilling execution, I'll go over some wells that are out there in the literature and stuff that can be pulled from public information. So the first one is the Shell Neely well. This was the first one done in 2019. it's successfully drilled and cased in the Wolfcamp A. They had a pretty high mud weight at 13.5, and I think it was because they were off of the stress orientation. Not for sure, but I think that's the case. The 6 3/4 lateral was drilled with a combination of rotary steerable and mud motor. And what happened is they were coming around here with the rotary steerable, and they weren't quite getting the dog legs they needed to stay on lease. So they pulled that and they went in with a mud motor and finished it off with the mud motor. The folks at Shell drilled this U lateral, and the idea was that the intermediate hole section was so problematic. What can we do to keep from drilling an intermediate hole section over here to get this lateral? And someone came up with the idea, let's turn it around and come back, and it was a great idea. The casing was run conventionally, and it was a liner. They didn't float it. They were prepared to rotate it, but went in the hole without rotation, so it was a great run for them. Second well here is the Chesapeake geolocation. This was done in 20. It was successfully drilled and cased in the Eagleford. When they were drilling here, they had some issues with wellbore instability and chunks of shale coming back. They had to increase their mud weight from 10 pounds to 11.3. So that is a potential issue with wellbore stability. All of the hole was drilled with mud motors, 8 3/4 lateral. This was based on an IADC SPE paper that I'm showing right here. And if you're thinking about drilling these U laterals, I would get on the website and buy a copy of this paper. It's a great paper. They did a great job. Their experience was very similar to my experience, and they explain a lot of stuff associated with that. Chesapeake did extensive torque and drag modeling to validate they were going to be successful. Casing was floated, and the numbers associated with drag were in alignment with their drag modeling. Turn wasn't completed. Can you turn on the laser pointer thing on this thing?
Oh, yeah.
It keeps turning off on me there. Thank you. The turn wasn't completed, so this part wasn't completed, but part of it was across the lease line, and then we have potential of the frac getting into the stuff that had already been completed over here. So they just did from here back and from here back. A key point in their paper was that the production out of this U lateral was the same as a 2-mile lateral based on completed footage. So when they take into account the lateral length, they would not include this because they didn't complete it. Here's an old Monarch location that PDC did. There were 4 wells planned in this section. 3 were successful. This is a Wolfcamp A, Wolfcamp A, Wolfcamp A, and this is a Wolfcamp B well. It was drilled about 70 degrees into the turn and was completed as a 1-mile lateral. The formation that was lost there was captured with another 1-mile lateral that went up right through here. So here's a Matador JJ Wheat well. My understanding from talking to people was they had wellbore instability out here in the turn, and they had to sidetrack the well and come back and finish it off. So the type of dog legs that they had on this well, the original open hole 10 to 12 and the sidetrack 9 to 12s. And here's an important slide looking at stress in the wellbore. So I've got a U lateral here coming back to the TD, and then I showed the fracture orientation associated with the completion stage. There isn't the right number in here, but you get the idea. And then I've got some of these stress things in here. And the key thing is when we're drilling in the right orientation, the fracs are going to be perpendicular to the wellbore. When we do that, we're drilling into the minimum stress. So the stress difference is the maximum stress with the vertical stress. So the vertical stress minus the maximum stress is a small number, or at least smaller than the other one. When we come around the turn here, all of a sudden we're drilling into the maximum horizontal stress. So the difference is the vertical stress minus the minimum horizontal stress. So we got a bigger stress difference there, which means that we're squeezing that wellbore. It's not being supported from the side, so you're more likely to have breakouts. So that is the reason you might have wellbore instability going around the turn. Now, with that said, I've only been able to find 3 wells where that was an issue, and most wells don't seem to have an issue with instability. But it is a consideration. So what is the consideration? If you have instability, you need to be able to increase your mud weight. If you want to increase your mud weight, you need to make sure your casing shoe is good enough to take it. So what might have been acceptable for a 1 mile or a 2 mile lateral may not be acceptable for a U lateral. So you just need to evaluate that. Here's another concern, and not necessarily completely intuitive. We've got depletion here, and this may be the case in a lot of situations where you have a stranded section, and it's stranded because people have already drilled wells to the north of you and to the south of you. So you've got depletion here. Now you've got to consider, what is this depletion doing to my heel? And if that depletion isn't covered with my intermediate pipe, might that create a lost circulation issue drilling this well? And maybe it isn't a problem drilling out, but if you have to increase the mud weight here, would it create an issue when you increase the mud weight for potential hole instability? So it's a consideration. The second one up here, you can see all these wells that are shown has depleted here at the section line. And if we were drilling a 1 mile lateral, you drill up here, and if you lose returns, you just plug it off the end of the wellbore and run your casing. But if you're doing a U lateral and you drill here and you lose returns, if you can't heal it, you're in a real bind. So you're praying that your lost circulation material is going to work for you. If it doesn't, and you want to keep going, that means you're just pumping mud away. And my experience has been all with oil-based mud, and it just is not going to work. So you need to consider, hey, how far away do I need to be from this completion so I don't have lost returns? If you do, you would run your pipe to right here and complete this as a 1 mile lateral and have to come over and catch that. But all of a sudden, if it's the Delaware Basin, you went from 53% rate of return to a 23% rate of return. So you need to figure out what it takes to be successful and not have lost circulation. And that is a qualitative judgment there. Here's another thing that isn't quite intuitive, but it is important, is the steering complexity of going around the turn. And I'm going to kind of step through this thing. So we're drilling out, going leg, and we're going down dip, and we're all familiar with that. But when we go around the turn here, we're going down dip, and now we're going across dip. So we went from going down to going horizontal. And then we come around here, and now we're going up dip, and we're going up dip, and then likewise going up dip. So this is what it might look like if you were to flatten everything out. You're going down, and then you flatten out, and then you're going up, and then it levels off a little bit. Now, that doesn't look bad, but your DDs and your consultants, the G&G team, the geosteers, need to have a map in their mind of what they're doing here so that they aren't just blindly drilling ahead. They know they got to turn because that's the directional plan, but they got to be sure to know that they're going to be leveling out where you potentially could drill out the bottom of your formation. So let's say you do that. You drill out the bottom, you drill through a limestone, it kicks you off even farther down. Now you're having to do your 8s or your 10s, and you have to get back up to the line in the formation that you want to be. So not a good situation. You just need to have a plan to execute on this. So drilling insights. Plan BHAs for each part of your lateral section. Have backups available if your dog legs aren't achieved. Set your dogleg limitations for each hole section based on your torque and drag planning. Torque and drag is really important. The beauty of straight laterals is we could go from 1 to 1.5 to 2, and it was an incremental thing. But when we do the U laterals, it's not an incremental thing. We are going for the whole enchilada, so to speak. So we just need to run the modeling to be sure that we're going to be successful. Include the DDs and consultants in the term planning meeting prior to drilling the well. This is about communication, and it needs to be with the whole team, in particular these guys here, because they're doing the work out there. Have a turn meeting with the DDs, consultants, geosteers, mudloggers, geologists, engineer, while drilling the outgoing leg. So sometimes we have meetings and then people on the rig change and they weren't a part of the meeting. So this one is really critical going around the turn. You want to remind everybody what we're trying to achieve and make sure that they're all on board. And there are a bunch of people here, but they're all critical to making this work. Have a survey projection process in place for the turn. So obviously your directional company's got great software to make that happen, but the engineer also needs to have some way of doing that. Just like with a curve, you're coming down and you're landing that thing. If you aren't getting your dog legs, then you need to know, hey, what a point do I stop trying to hope that we're going to get there, and I pull it with another assembly in my hip pocket that can be successful. The same thing here. You need to be able to project ahead where to call it quits so that you don't violate the lease line. You don't want to be in a situation where you drill so far that now you don't have anything that can get you there, and then you got to trip out a hole and sidetrack it. Better to trip out and pick up a bigger bend motor to get you inside your lease line. Have the right drill pipe. That's based on the torque and drag stuff. The top drive that will support that, and an iron roughneck that will be able to break your pipe when you're coming out of the hole. Plan the casing run and have the mitigation in place with tools and tubulars to be successful. So the regular running a casing probably is challenging on most of these wells. Floating is probably going to be successful, but with the new wells that are coming out here that are 1.5 miles up, 1.5 miles back, 2 miles up, 1 mile back, maybe you need to have a rotation plan in place to guarantee that you're going to be successful. Communicate these torque and drag expectations to the rig personnel so they know what's coming at them, so they don't think crazy things are happening. And success out there is really dependent on teamwork and communications, G&G, drilling engineer, consultants, rig contractor, directional drilling, geosteers, and planning. So it takes a bunch of people, and they need to be a part of it because we're all interfacing to make this turn work. So completions, this isn't my expertise, but I've been around some of this stuff, so I'll go over a few points here with it. Long strings and liners have been used successfully. The zonal isolation seems to be dominated by cementing. Plug and perf using zipper fracs is widely used. Leg separation will be determined by the G&G team and practical considerations. So if the G&G team says, oh, we want it 800 feet apart, and the dog legs are too bad in the turn, well, then maybe you do it 1,600 feet apart and you kind of nest or overlap these U's. So that is something where the asset team works together to make that happen so that the drillers have reasonable parameters they can work with. Planning work is required for wireline and coil tubing sizing. Your vendors will be able to run the drag models. You might want an electric disconnect on the return leg on these tools, wireline tools, because you may not be able to pull loose if you want to. History has shown that the completions have been relatively trouble-free, and that's what I've heard talking to numerous people. It wasn't that big of an issue. Dissolvable plugs may be justified in the return leg if there's any issue drilling things out. They will disappear with time. Production per completed lateral foot is the same for U laterals and 2-mile laterals. So there is some information out there on this. I've mentioned the Chesapeake paper. I've talked to operators that have said the same thing. I would say evaluate the U for potential completion stages and casing risk. So some people don't complete the U. Some people complete part of the U partway in. You need to draw it on paper, put the frac orientation on there, and physically lay out where the stages are to see if this can be worthwhile or not. In Texas, the U doesn't get to go to 100 feet from the lease line. It's 330 feet, and somebody out there needs to hit up the Railroad Commission about wasting the resource. But that takes up a fair chunk of the U. If you're building on 10s, 571 feet minus the 330. Let me come here. So here's some information that Enverus sent to me, and I appreciate them giving it to me. So we've got 3 basins here, looking at U lateral performance in red, and then straight 2-mile lateral performance. And based on this, it says, oh, the Delaware, the U lateral is the same as a 2-mile lateral based on completed foot. The DJ is underperforming a little bit, and the Eagle Ford is way overperforming. And the only one I believe is this one right here. This underperformance could have been a parent-daughter thing. This overperformance was in an undrilled section, so there was no parent-daughter, and this was parent-daughter related. So when they did this, they did 5-mile radius, I believe, to pull this. And I know formations can change in less than 5 miles. And in my mind, there is not any good reason I can think of why a completed lateral foot in a U lateral would be any different than a 2-mile lateral. But, I'm not a reservoir guy. So here's Enverus stuff. Chesapeake paper said that it's the same foot per foot. Theoretical work from a paper that's out there on modeling horseshoe wells says that it's effectively the same. And I've confirmed this with numerous conversations with operators. So patent considerations. Shell does have a patent on this technology. Here's the first sheet of the patent. What to do about the patent? I've talked to a lot of folks. Some pretend it doesn't exist. Some assume it can't be enforced. There was a point in time where you could avoid the patent claims by pulling back from the lease line or changing formations. My understanding is the patent has been tightened up, so that's not available anymore. Demonstrate the patent is invalid due to prior art. If you have the prior art, that's great. If you don't have the prior art, that could be a problem. The final thing is Shell is licensing the patent through WorkRise. So that is another potential thing. I've talked to some operators where their entire company headcount is less than what Shell's patent office is. So taking on Shell with the legal parts of this could be intimidating for a little operator. I do know some people that have said that they do have prior art and are not interested in paying the license fee. So I'm going to come back to where I started at, stranded sections. This is what makes U lateral work. If you have stranded sections, executing on U laterals, drilling and completions, and this is a team deal. If drilling wins and completion doesn't, it's a big fat failure. It needs to be a core competency if you have stranded sections. And if you aren't doing this and you have stranded sections, you are burning money like crazy. So is it $3 million, $3.5 million, $4 million? $5 million was probably too high as initial estimate from Matador, but you are burning a lot of money. Your investors deserve better. And on this website, udriller.com, there's information on where these U lateral wells are at, some of the stuff I showed you with the map, and a list of wells that's out there for your viewing. I think that's all I got, David.
All right, well, let's go ahead and over here, I'll take that off. We'll go to camera 2 here. All right. Oh, is that camera frozen? Head back to stage. Why is it not doing? All right, well, let's just we're gonna at least keep you on the screen there.
We can get chummy.
And do some quick little troubleshooting here. So we'll just turn that one off. Turn that one back on. And in the meantime, we can go ahead and I'll just star a bunch of these just so that we don't lose our place as that's coming back on. Oh, that wasn't a question. And we've got a lot of questions that have come in. There we go. Like fatigue, any sections coming. Okay, and I think that's outside of the US. Okay. All right, guys. Yeah, if y'all have got any questions, go ahead and start throwing them in. I've got everything starred. Let's see. Oh, it's working now. There we go.
Right.
And just to be able to help with the colors, color correction there. All right, guys. So yeah, we'll go ahead and first question here, right? Robert, curious the approximate number of days drill U lateral versus the time to drill 2 lateral wells.
You know, I would have to refer back to my notes on that. I do know going from a 2-mile lateral to a U, the additional time in the curve with mud motors and BHA trips is about 5 days. And I don't have my notebook in front of me, but obviously the times were used to calculate the cost difference, and the cost difference was about $2 million. Shoot, I don't have an answer for you on that. I would have to get back to you. Can you write a note down and we can post it later?
All right, so we'll say
how many days to 1 mile versus U?
All right. So here's one about the patent.
What point does it become a U? You know, if you read the patent, I think it goes past 90 degrees to 270 degrees. It's kind of like everything in there. On that U-driller website, you can go and look up the patent and download the thing and read it for yourself. You might give it to a lawyer. So reading patents is not the most fun thing in the world.
On the patent stuff, I would say, I think I could invalidate it.
Yeah.
Because, you know, obviously not being a patent lawyer,
yeah.
But if you are to patent something, you have to be able to keep everything kind of secret.
Yeah.
They filed their surveys with the Texas Railroad Commission, which made all of the information about the surveys public.
Yeah.
Prior to filing the patent.
Yeah.
So
is that true?
Yeah.
Okay. Then that would be enough, I think.
I mean,
so get your patent lawyer to check it out and
yes. I mean, I would just tell everybody don't pay for it. I mean, it could be, to me, easily invalidated.
Yeah.
Next one from John Wart. Some things should not be patented. Why impede? Let me do this real quick. Stop that screen. Okay. Why impede industry progress as we compete in the energy transition?
Yeah, for sure.
Lost ourselves again here.
You know, for sure. Shell came up with the idea. Patents is about compensating people for good ideas. Whether they can enforce it or not, I don't know. But I'll tell you, it was a heck of a good idea, and it's an invaluable idea.
Let's see here. Sorry, getting the other camera set up. No, I mean,
click on that one.
Yeah, not hard.
Okay, to that point, if completions, etc., see little to no additional trouble when working on a U lateral compared to schistral one, maybe it shows how much we are hiding in straight laterals. I guess that's a comment.
I guess so. Oh, he was talking to John.
Oh, very good.
Maybe John had a question and he was answering back to him.
How much work do you do with the bit manufacturer beforehand? All of that. You know, you're looking for something that is going to perform kind of like a curve bit. So if you want to make it as friendly as possible for your DDs, pick something similar to a curve bit. And, you know, that's part of the planning process. You're talking to your DDs, you're talking to your consultants. What are the tools that are going to make us most likely to be successful? They'll provide you input on what bits to use. And of course, as drilling engineers, you know what's been successful drilling your curves. That would be a good place to start. And then over time, I'm sure there are going to be developments that would point to bits that might be more successful on the turn than what would be a conventional curve bit.
Sorry, guys, trying to fix everything behind the scenes here.
It sounds like operators are running conventional spacing 90 feet for borehole surveys. As you referred to standard dogleg measurements, if correct, why are they not running continuous 1-foot surveys to truly see the tortuosity of the wellbore, in which it is critical to torque and drag plus pipe buckling calculations? You know, we're kind of old dogs in drilling, and maybe that's where we need to be going. It has been my experience that there's something going on with the smaller tortuosity that's not displayed with surveys. Maybe this will be something that happens in the future, but we're all creatures of habit. We've been doing 90-foot, and that's what we've done on these also. Let's see.
All right, next one here.
Has anyone run borehole imaging tools to see the real borehole shape along each section? I'm not aware of any. Certainly, we all know that they're out there. I don't know why this would be any different than what we've seen before. I am a big fan of the reamers because I've had previous experience with rotary steerables. You drill the TD in a straight lateral and have problems pulling out of the hole. And I think that's because you create that circular bit pattern, and when you pull out of the hole, the blades on the bit aren't rotating backwards, so you have resistance pulling out. After running these reamers, it was much easier to pull out of the hole. Now, I can't remember who the reamer vendor was, but this fellow showed me surveys of no reamer, and it showed it to be a little under gauge, and I think that was the bit pattern. And then he showed me the caliper log after using their reamer, and it showed it a tiny little bit over gauge. And I think that is just the reamer taking off the bit pattern to make it easier to get out of the hole. And I think that's happening in these U laterals, in particular in the U, because we are doing a horrendous amount of directional work in that thing. You're sliding 50, 60, 70% of the time, and then following with straight courses in there. And it just makes it a very rough wellbore that generates a lot of friction. So I think that reamer is really important there. So you can drill across the lease. You can drill across the lease lines as long as you do not produce from the whole section that crosses the lease line. You know, you can't. In that particular case with Chesapeake, they own the leases over there. So it's really a big deal, at least where I worked in Texas. If you go across that lease line, you've got a real problem, as you got somebody that can mess with your business. And that's the guy on the other side. They can tell you what to do, and they have huge leverage on you. The other thing is if you complete within that 330 feet of the lease line, it's the same thing. All of a sudden, you got somebody across the lease line that can mess with you, and nobody wants to be in that situation. So if it looks like you might cross the lease line, you got to trip out of the hole and get a BHA that's going to keep you inside of it. Because nobody wants to have to ask permission of the guy across the lease line to produce your own well.
Right. Oh wait, this is in one. Sorry, unstar that one. There we go. From Mackenzie.
Okay, most of the economics reported by E&P compare against 1-milers on a footage basis, but have economics then compared to 2-milers on a BOE productivity basis. Is there enough production data to say that the economics are better than 2-mile wells? So U Laterals do not compete with 2-mile straight laterals. This is a stranded section tool that takes you from the economics of 1-milers to the economics more than halfway up to what you have with 2-milers. So if you have two sections put together, clearly you want to drill a 2-mile lateral. If you have a stranded section, you drill a 1-mile lateral, the economics are lousy, and the U lateral will bump it. In the Delaware Basin, my rough estimate was about 30%. I recently checked out in the DJ Basin, and the 1-mile laterals were like 40% rate of return, and the U lateral was like a 90% rate of return. And that really surprised me, because I thought with the drilling being easier, there would be less cost savings. And I was so surprised that I called a friend that works for an operator and asked him, hey, what are the numbers? And he confirmed that that's the case. You get that kind of a bump.
All right. Thank you for your question, Mackenzie. Now on to Taylor.
Have you tried drilling curve, outgoing leg, kick off the turn before tripping to see what all you can get with the
Curve
lateral BHA? Are you always making a dedicated turn BHA? Had not considered the reamers before. Interested to see what you say to Pete's question. So there have been one and done runs that have done the whole thing, and that's the one I'm aware of is rotary steerable. They cruised out, did the outgoing leg, did the turn, and came back, and it was a very long lateral, so they needed to be able to rotate all the way, or they were going to have a very difficult time. So yes, that certainly is possible. And then, let's say you're out there drilling the turn, and everything's going great, you're done with the turn. Do you trip that BHA, or do you keep going? And the temptation is really great to go ahead and do that. You have a little bit bigger bend motor in the hole, so you're putting a little bit more stress on it, and your directional company wants you to reduce the RPMs and all that type of stuff, but certainly we do that. So yeah, you don't have to make dedicated trips. I guess the good thing would be on your first well, just plan every section to be successful, and the carrot is very big. And then the next well, make it a little tighter, and maybe you get rid of a trip by using the BHA longer, something like that.
All right.
Is combining both U lateral drilling and geosteering feasible? Is this combination applied in the U.S.? What could be the most challenging problem in running this combination? So the geosteering on these laterals, we're doing that on all the wells. And usually it's pretty easy because the dip is relatively constant. So we're just bouncing the BHA up and down a little bit to stay in formation. The geosteering is really important going around the turn because of the geometry of it. So if you're going down dip, there's going to be flat dip, and there's going to be up dip. And it's good to have a mental map of this thing so you can be ready for it before you drill out the bottom or drill out the top. And I just say that because my experience in the Delaware Basin is you drill through a limestone and it'll kick you, and then you're way off. but you're still supposed to be making the turn. And now you got to get the BHA back to where it's supposed to be, which means you got to get through the limestone again. And there's a chance you'll bounce off of it instead of cutting through it. So it just makes it difficult if you don't really stay on top of where you're supposed to be.
I mean, you should have a pretty good idea since you just drilled through it. And you're drilling back on just the other side of it. So
yeah,
hopefully the geosteers know where they're at.
For sure. That's a thing for the guys on location to have an idea, the DDs in particular, to know, their surveys are behind them and what they're drilling is ahead of them. So they can't necessarily see it. It's a good idea to know, hey, things should be flattening out here. Things should be going up. Things should be going down.
All right. And then I believe it was either Taylor or McKenzie, I think, referenced this question here from Pete.
Have you seen U-turn BHAs in the turn and return with and without a reamer? I like your idea that it cleans up rugosity, but any runs that support improved hole with the reamers and BHAs. I'm trying to think if I've ever gone without them. I think I've run it on everything. And there's one experience I had where we went around the turn and the drilling just sliding ground to a halt. We could not slide anymore. No matter what the DDs did with the agitators and the oscillators, sliding would not go. So we cleaned up the hole, and it was 4 or 5 bottoms up, something like that, a whole bunch, way more than what it should have taken. And we went back to bottom, and it would not slide. And then we reamed that 500-600 feet, and it went back to sliding like it had before. So in my mind, that is proof that there is something going on with the wellbore quality that reamer was cleaning up. And maybe you could do that with the bit also. But the beauty of the reamer is that if you're rotating, let's say you're in the outgoing leg, you're rotating that thing all the time, you're rotating the head, right? So you're cleaning up the outgoing leg, you're cleaning up the return leg, and with the turn, I think you got to either do wiper trips, not great, or ream each stand down to address the hole quality issue.
All right. I bet anybody that sells reamers is going to love to hear that. All right. This one from Jerry Hudson.
So is the production casing high collapse? The stuff I've been around is 5.5 20 and 5.5 23 pound. So the collapse rating on that stuff is like super stout. I don't believe it was high collapse. And I think somebody probably knows better than me. I've been away from it for a year here. Is the 23 pound like 14,000 on the collapse, and 20 pound is 10 or 11. They're really high numbers, and much higher than obviously the compressive loads that we'd have at kind of the Delaware depths that I'm familiar with.
All right. John, another question from him.
How is the additional drill pipe fatigue addressed between the operator and the drilling contractor? It's kind of the same old thing. You go ahead and figure out how many feet you want to drill, and then you go ahead and inspect the pipe. And if you've ragged out their pipe, they make you pay for it. Now, I am not a fan of the drilling contractor's drill pipe with NC50 connections. And I'm a believer in running pipe, or if you got a progressive, I know that's a bad word, if you got a progressive drilling contractor, then the drilling contractor can provide you the high torque drill pipe. And I understand there are contractors doing that. So it's always been a beef with me that you run a rig, you get this NC50 drill pipe that doesn't have much capability for what we're doing anymore. And you say, oh, I'm going to rent pipe, and it costs you $3,000 a day to rent pipe. So you leave their stuff in the yard and they don't cut you a deal. There's no price cut for not using their pipe. So if you can get your drilling contractor to do that, you'll save money for sure.
All right. Any comments on frac design execution differences between the 2 mile laterals and U-turns?
You know, I wish I knew something about that, but really I don't. I just haven't been involved with it. I'll have to go find a completions friend that isn't hooked up with PDC or Chevron where they're free to talk to me.
So we've got U-driller, and then we need U-completer.
We do for sure. Tell them to give me a call.
Yeah. This one kind of goes into the same fold, but maybe a little bit broader question.
Is the completion plan the same in the U versus the 2 lateral sections? You know, the difference is if you have 2 1 mile laterals, your zipper back and forth on those. But if you have a U, you got to do this part and then you got to do that part. Now, you can overlap these U's, and that reduces the dog legs you need in the turn. And that is a strategy that I've certainly seen a lot before. So that's where we need the U completions guy to have more detail on that.
When we find him, we'll get him on the show. Yeah. Final one here. I wonder how long it would take, or how long it will be before attempts are made to drill a double U well using 2 U-turns in a single well. Silly now, maybe, but with technology, then who knows? So I'm guessing that would be, so we go up and then back down. So it's like an S.
Yeah.
But we can't call it an S-shaped well because that's a directional well. A flat S.
Yeah. You know, I've looked at that before, and it comes with more torque and drag. So the engineering has to be done. Probably, there have been wells that are 1.5 miles up and 1.5 miles back. An operator has asked me to do some modeling on 2 miles up and 2 miles back. So it's like anything. We started with these horizontals at 1 mile, and now we're doing 4 miles. So it will be intensive engineering work to make it work, but for sure, your imagination is going to, I think, be what limits us in the near term, and then farther out, then there will be physical limitations.
All right. Well, I think that's all the questions for today, unless you guys got any more while I am wrapping up the show. John, if you'll switch spots with me real quick. All right, guys. Many thanks. Okay. Why does it keep doing that? I don't know. I think these GoPros are just getting hot. I think that's the case there. All right, guys, if y'all have any more questions, feel free to throw them into the comment section. 2 things when I ask you guys to do, tag a friend, somebody that you think would get a lot of value out of today's presentation, as well as, if I can get squared away here, like I said, our sponsor for today's show is #AIDRILLER. Go ahead and put that in. Do see we have a couple more comments. I'll take that one off, put this one back on, jump back over here. Yes, what was the comment there? Yes, I would think torque and drag would be prohibitive to do 2 U's in a well bore.
It isn't prohibitive, but it's worse. So you're going to get into more engineering. Obviously, the numbers are going to go up. You probably need to taper your drill string, and it's just a matter of doing your homework. Do the homework on it and see if it's possible. It'd be great to have some experience with just U's instead of going straight into something like that, so you have a track record to know how this is going to work for you. But yeah, I think it can be done. I would not say prohibitive. Difficult.
So we're going to go ahead and start patenting that this week, and then just throw a model of it up on LinkedIn. Or don't patent it and just throw it up there, so then it's for everybody.
For sure we can run a quick torque and drag model, and I'll shoot you something off.
There we go. We'll get that posted later this week. Just because I never really do this. Says, thank you, John. Insightful session. John says, great presentation. Thanks, John and David. Appreciate the presentation. It's from Taylor. Thank you, guys. Thanks, David. And then the ever famous LinkedIn user says, thank you for an interesting presentation, Q&A session. DG, keep up the good work. Oh, thank you. I never get those. All right. Let me go ahead and add this to the screen. Share screen, Chrome tab, giveaway tool. There we go. Share. And we'll add this to the stage. Take that one off. Yep, there we go. All right. Let's see who the lucky winner of today is. Thank you guys for joining in. We've got a 3D printed drill bit for whoever it is. And our lucky winner is Richard Brainerd. Richard, thank you, sir. Has Richard won before? I think he has. I don't know. I have to look. I don't know. Regardless, you keep watching the show, you keep winning stuff. I got no problem with that, as long as it's not me or Tracy or my mom. Because they get all the free stuff all the time. All right, guys, thank you all so much for watching this week. We do appreciate it. Next week, no show next week. I am doing the IADC general meeting next week, and I'm presenting at that. So I won't be able to do the show. A week after that, let me see. I've got my little cheat sheet of notes here. Oh, yeah, November 22nd, David Ransom Wood will be coming on. He is actually banned from LinkedIn, so this is the only chance you'll probably be able to get him to see him on LinkedIn. The week after that, December 6th, Michael Bohonik will be on, and then the week after that, Abraham Montez. So absolutely amazing lineup for the rest of the year. If you are interested in being able to sponsor the show, none of those will be sponsors, but those will all be very highly watched shows. Feel free to be able to get in touch with me. Love to be able to have a sponsor for those episodes. That's really it for me. John, thank you so much for being here today. Really, really, really do appreciate it. I'll find the little button here. That's it for me. Everybody have an absolutely amazing, amazing weekend. Thank you guys all so much. And as always, know your industry.